Okay, so maybe I'll just go over the details of the test once again for everyone who's here. So once again, there is a test on Friday. You need to come to class at 9:20 and be inside the Zoom call that I will set up. It's just going to be like every other Zoom call, but you need to have your cameras on so that I can try to proctor this exam. You will access the exam on Sakai under the tests and quizzes tab. There will be a document that you can download. Then you should do your work on your own paper. And at the end of the class period at 10:10, you should take photos or make PDFs of your, actually taking photos will be fine. So you can take photos of your documents that you've produced for the test and then upload them to Gradescope, and that's how I'll grade them. If you are in a different time zone and you can't be present at the class time, you need to send me an email so that I'm aware of what's going on, and then I'll send you more specific instructions. Lastly, the material that will be covered on the exam will be essentially everything that we've covered so far, including the very end or the very beginning of 1.7. So direct proofs using evens and odds will be expected. Is there a question? Will what we cover today be on the exam? Only what we cover at the very beginning of today. So I'm going to start off today by doing some direct proofs that are pretty straightforward, that are similar to what I did on Friday. And those are fair game, but the rest of the stuff, when we start doing proof by contrapositive or proof by contradiction, will not be on the exam. So another way to say it is that your homework today involved some problems from the beginning of chapter 1.7. The questions that I could ask you on the exam are similar to the ones that you've already done homework on. I won't ask you a question that you haven't done homework on. Does that clarify things a little bit? What will the format of the test be? So I believe there are 6 or 7 questions, and all of them are open questions. That is, you will have to write things similar to the homework. You'll have to do some translations of propositions. You'll have to write out an argument, stuff like that. So I would expect it to take up, you know, maybe a sheet of paper for each pair of problems or something like that. So similar to what you've gotten on the homework. So I will provide a cheat sheet as the first page of the exam, and that is what you will have available to you.
Do we know what's going to be on the cheat sheet yet or no?
Yeah, the cheat sheet will be the following tables. The cheat sheet will be the list of logical equivalences and their names, which is page 29 in the textbook, the table of logical equivalences. And also it will be the table of valid arguments, which is, where is it? It's the rules of inference table on page 76. So those 2 tables will be provided to you, as well as the implication substitution for logical equivalence. Any further questions? Will we have the instantiation ones? Yeah, universal instantiation or existential instantiation is fair game. Oh, those won't be on the cheat. Will they be on the cheat sheet? Yeah, I should put those on the cheat sheet. I should put those on the cheat sheet. Okay. Any further questions? Okay, it sounds like y'all are all questioned out. So let's move on to proofs. So now we're in 1.7 proofs. And we're doing proofs with a kind of small list of mathematical, oh, is there a question? We're doing proofs with kind of a small number of mathematical definitions, basically. So the direct proofs, the idea behind them is as follows, essentially. I'm going to draw the truth table here really quick. PQ, we know that the truth table is true, true, false, false, true, false, true, false. And then the final statement, P implies Q, has the truth table true, false, true, true, right? So as an aside, when we use a direct proof to show a statement of the form P implies Q is true, a viable technique is to show that if we assume P, that Q can never be false. Right? Because the only time when P implies Q is not true, or the only time when P implies Q is false, is when P is true and Q is false. So if I want to show that the statement P implies Q is always true, it is sufficient to show that this case can never happen. I can never have Q true and P true and Q false. So the technique of proof is you assume P is true and you show that Q has to be true as well. And that's the idea behind a direct proof. Any questions on the structure of this argument? Okay. Then what we'll do next is we'll do a bunch of examples because examples are very important here. So let's do the following example. And I don't know if you did this on your homework or not. If you did, then it'll be fast. Show that the square of an even number is even. Did you do this on your homework? Yes? Okay, that means that it'll go well. So I want to now write this out very carefully in terms of a proof. So maybe y'all can help me along. How should I prove this statement? Yes, first we should let n be an even number. Let n be an even integer. By the definition of even, what do I get? Yes, n is equal to 2k for some integer k. N is equal to 2k for some k in z. This is by the definition of even. And then n squared is equal to 2k squared. And if I distribute the power, that's the same as 4k squared. Very good. But 4k squared is equal to 2 times 2k squared, and thus is even. This concludes the proof. Then I'll put a little box here to say, I have finished the proof. So once again, and I'm sure you all know this because you all did this on the homework, but the point is, I want to show that n being even, which is the statement P, implies n squared is even, which is the statement Q. And the way that I did that is I showed that it is never the case that I have P true and Q false. So I took an arbitrary even number, and then I checked its square and saw that indeed its square is even. So true, false never appears, so the proposition P implies Q is true. Any questions here?
Is it sufficient just to say by the definition of even, or do you have to, like, would it be a good idea to give the definition of what even is?
So here I am, so I don't quite understand your question.
In the what's it called? It's like the explanation. It says by definition of even, meaning like what's like by the definition of what an even number is. But do we have to explain that? Because I know in the homework I said anything multiplied by 2 is an even number, so this is an even number. Would I have to do that, or can I just say by definition of even?
You can just say by definition of even, n is equal to 2k for some k and z, because this is precisely what it means. Yeah, so you have to use the definition when you're making such a translation. Probably
Okay.
what you wrote is correct. All I want to underline here is that the reason that I can write n is equal to 2k for some integer k is by the definition of n being even.
Okay, that makes sense.
That's the step that allows me to proceed. Okay, probably this is another one that you did in your homework, but it's a good idea to write formal proofs and to write them often. So the next one by direct proof is prove if x is rational and x is not equal to 0, then 1 over x is rational. Was this on your homework as well? No? Okay. So once again, we're going to be in the same position. How do I start off this proof?
Would you do the definition of irrational again?
Yes, I definitely need to use the definition of rational. And the first thing that I'm going to do is I'm going to assume that x is a rational number, right? In my head, I'm thinking universal instantiation. I don't take it, but let x be a non-zero rational number. And then what is the definition of a non-zero rational number? So then by definition of rational, what can I say? What's the definition of a rational number?
It's divided by something?
That's close. So it can be written as a ratio is perhaps the way that I would try to remember it. So by the definition of rational, x can be written as p over q for p and q in z, q not equal to 0. This is just the definition of rational. What else can I get? Can p be 0?
No, because then x would be 0.
Exactly. So x can be written as p over q with p and q in the integers, q not equal to 0. And since x is non-zero, p is also not equal to 0. So by the definition of a rational number and by being non-zero, I know that I can write x as a fraction p over q, where p and q are both not zero integers. Okay? Then, now that I know what x is, I need to figure out what 1 over x is. Then 1 over x is equal to what? Yeah, it's equal to 1 over parentheses p over q. But what's 1 over a fraction? As has already been written, this is the same thing as q over p, where p is not equal to 0. Thus, what?
Thus, it's rational.
Exactly. Thus, 1 over x is rational. Very good. And then I finish the proof with either a box or a QED if you want. You can write QED to finish off proofs. I usually use the box. QED is some old Latin. We don't need any more Latin. We're done with that. Any questions on this? Why the box and not 3 dots? So the 3 dots is technically a shorthand for therefore. So I don't want to finish a proof by the word therefore. I want to finish a proof. Technically in Latin, this is quod erat demonstratum, which is essentially saying, thus what was to be shown is shown. And then the box is a shorthand for that. I have shown what I was trying to show. But the 3 dots being therefore are not the end of the sentence. Yeah, Latin's cool. I'm not dissing Latin. You know, it helps you understand Romance languages, which is cool enough. Any further questions on this? So now that you know that questions like this using direct proofs will be, what is our limits for mathematical shorthand notation? That is a delicate question. That's a question of taste, and that's where we kind of enter into the style of mathematical writing. Here's the idea when you're thinking about how much notation to use. You should always use full sentences. So notice that when I write these things, even if I have symbols inside them, I'm still writing full sentences, because here, this translates to, then by the definition of rational, x is equal to p over q for p and q integers and q not equal to 0. And so here there are a bunch of symbols, but when I say these symbols out loud, they form a part of the sentence. And then I conclude the sentence, and since x is non-zero, p is not equal to 0. So what I would say is that whenever you're thinking about writing something down, you should always write down full sentences. And then if you use some notation, that has to make sense when you say it in a sentence. Hopefully that's at least a helpful guide. And we'll discuss style of mathematical writing as we continue in this class, but at least that's a start. Okay, so for these direct proofs, are y'all feeling a little more comfortable with how they start? Now you've kind of seen that if we're doing a direct proof, we always start with let x be such and such. Then we use the definition. Then we look at the final thing and show that it also satisfies some other definition. Like, is that feeling okay? There's a trend in these proofs, right? Okay. Let me see if, let's do one more. Should we do one more, or should we move on to contrapositive? One more it is. Okay. Let's do the following. Let's show that if n and m are perfect squares, here n and m in Z are perfect squares, then n times m is a perfect square. Is this homework? No? Great. Excellent. So how should I start?
The definition of a perfect square. So let two integers.
Yeah. So first I'm going to start with let. Let's a great first word to start off these proofs. I'm going to do the universal instantiation where I take two perfect squares. I take two integers that satisfy the premise. So let n and m in Z be perfect squares. And then, exactly as you said, Christian, I then take the definition of what it means to be a perfect square. By the definition of perfect square, what can I do?
Can do n equals a squared and b equals and m equals b squared for any a and b and z.
Exactly. Well, not for any a and b and z. There's a particular a and a particular b that do the trick. So I'll write it as follows. There exist a and b in Z such that a squared is equal to n and b squared is equal to m. I'm sure this is what you meant, right?
Sure.
Right? The definition of a perfect square means that there's some other integer such that you square to get this thing. Okay, and what can we do next? Yes, Morgan, I've got precisely that. There exist A and B and Z such that this following holds. Yep. Right, now we examine, then n times m is exactly equal to a squared times b squared, which I can then rewrite using our rules of exponents as what? Perfect. It's equal to ab squared. Thus, mn is a perfect square. And then I draw a perfect square. Feels great doing these proofs, doesn't it? It's very enjoyable. Any questions on this one? Is that an example of a difficult one? The only difficulty that's in here is the fact that instead of just taking one thing as a premise, is that I start with two conditions, right? I start with two perfect squares, n and m. And so then when I use the definition, I've got several variables floating around. So I wouldn't say that this is a difficult one, but it does illustrate another kind of thing that you need to take care of, because thus far we've always been working with just one integer or one rational number or something like that. Yeah, I'm going to say that that is not necessary, because what the statement that we're using there is that you can multiply two integers and stay an integer, and we're going to take that as known. So we're going to take as known the fact that you can add, subtract, and multiply in integers, in rational numbers, or in real numbers, and stay inside the integers, the rational numbers, the real numbers. Yeah, we can take that as a known fact. But you're right. If I wanted to be very pedantic, I would have to say, look, AB is an integer, therefore MN does satisfy this thing. You're right. That's a good point. Any further questions? Okay, let's carry on to another proof technique, which is very nearly the same and yet somehow subtly different. But, you know, really mostly the same. Okay. This next technique is as follows. This is proof by contrapositive. And the idea here is that, once again, we want to prove that a statement like P implies Q is true. And what we've done thus far is we've examined the truth table, and we've said, well, it's sufficient to show that whenever we assume P is true, Q has to be true as well, because then we exclude the only case in the truth table of P implies Q where P implies Q is false, right? Another technique is, remember, what is the contrapositive of P implies Q? Not Q implies not P. Perfect. So remember that P implies Q is logically equivalent to not Q implies not P. So we can do the same thing for not Q implies not P. If we want to show, P implies Q is always true, then it would suffice to show not Q implies not P is always true. And then we can do the exact same thing here. You can show, to show not Q implies not P is always true. What's the one case that you have to rule out? You have to rule out this proposition being true and this proposition being false, right? Because if the hypothesis is true and the conclusion is false, then the whole implication is false. So what we want to show is that if we assume not Q, then we must have not P. So show if not Q is true, then not P is true. And this is enough. If you show that not Q is true, then not P is forced to be true, then this whole proposition is true, which by logical equivalence implies this proposition is true. Does this help? Is anyone confused by what I've said? If you're confused, that's fine, because we're about to do a bunch of examples, and that should help. Thank you, Mahita. That's I'm very happy to have a little bit of feedback. So what I would ask is that you tell me if you're still a little confused after we do one example. And if you are, I've got 2 more examples, so we're in good shape. Okay, example. Prove that if x is irrational, then 1 over x is irrational. Okay, here is a first hint about this. If we try to prove this directly, how would we start? So here, this is not going to be the proof. I'm going to do little lines here to show like discussion. Yeah, exactly. If we wanted to try to prove this directly, we'd start with let x be an irrational number. What's the definition of an irrational number? Right, exactly. The definition of an irrational number is that x is not rational. So what I can say here is x cannot be written as p over q, p, q in z, q not equal to 0, right? All I know is that x cannot be written in this way. This doesn't really tell me anything about how I can write x, right? Like I'm kind of stuck here. Because in all of my previous proofs, I've been able to say, oh, since it's a perfect square, then I can rewrite it this way. Since it's odd, I can rewrite it this way. Since it's rational, I can rewrite it this way. Here, all this is telling me is the negation of one of those things. But I kind of can't use this to rewrite x in any nice way. Do you kind of see where I'm stuck? So, since I'm stuck with direct proof here, what I could try is I could try to prove the contrapositive of this statement. And if I prove the contrapositive, that'll be the same as proving this. So here this is P implies Q, where P being x is irrational and Q being 1 over x is irrational. But the contrapositive is precisely the following. Show that if 1 over x is not irrational, namely 1 over x is rational, then x is rational. Do you agree that what I've done is I've taken the contrapositive of this statement and written it here? So here we started with, I'll just write it formally. P of x means x is rational, or x is irrational. And then here, q of x is 1 over x is irrational. So what we were asked to prove up here is P implies Q, but that's logically equivalent to not Q of x implies not P of x. And not Q of x is the statement 1 over x is rational, and not P of x is rational. And now this statement is going to be easier to prove, right? Because if we know that 1 over x is rational, then we can say something positive about it. We can actually rewrite 1 over x as something different. So when we actually do the proof, we will do the following. So proof, whenever we don't use a direct proof, we should mention which indirect proof method we are using. So we use proof by contraposition. So we show that if 1 over x is rational, then x is rational. So I've written that down, the contrapositive of what I was first starting to prove. And now what do I do? Yep, exactly. So let 1 over x be a rational number. By definition of rational, one over x can be written as p over q for q, p, q in z, and q not equal to 0. And now what is x? Then x is equal to 1 over x, which is equal to x, but I want to use my alternate description, right? I want to use the fact that it's q over p, right? Because I'm trying to show that it is rational. So this is equal to q over p for q. So what's the last thing that I need to check? If I want to claim that a ratio of two integers is a rational number, well, I need both p and q to be integers, but what else do I need?
To be non-zero.
I need the denominator to be non-zero. Why is p not 0?
Because it'll be in the denominator and you can't have a 0 in the denominator.
So that's kind of true. My idea is that I know that 1 over x is equal to p over q. And my question is, if p were 0, what would break with this equation? Exactly. 1 over x can never be 0. Since 1 over x cannot be 0, we see that p is not equal to 0. Yeah, exactly. If 1 over x was equal to 0, then you'd have 1 being equal to x times 0, but anything times 0 is always equal to 0. So I have to use kind of information that I got here to verify the last part of what it means to be rational. Since 1 over x cannot be 0, we see that p is not equal to 0, thus x is rational. And that finishes the proof. Okay, so this one was a little more challenging for two reasons. There were two things happening here. One is that we used contrapositive for the first time, and the second was we had to kind of verify an additional piece of information before we could say that indeed x was rational. Any questions here?
So using the contraposition, is that just making the question be framed in such a way that we can use the direct proof?
Yes, that's a good way of thinking about it. I got stuck on the direct proof for P implies Q, but I know P implies Q is equivalent to not Q implies not P, and this was an easy, I could use direct proof here because here, assuming that something is rational tells me something positive that I can use about a number, right? In other words, I'm agreeing with your assessment. I agree that using contrapositive makes it so that I could use a direct proof in some constructive way for one of my directions. 0 is a rational number. 0 is a rational number because 0 is equal to 0 over 1, right? And this is a rational number because the denominator is not 0. Right, so let's work out the following. So assume, well, let me not prove this, but let me just discuss. So if 1 over x was equal to 0, then this would imply, so note x can't be 0, right? We never let zeros be our denominators. So if 1 over x was equal to 0, then I would have 1 is equal to x times 0. But what is x times 0? Yeah, I can never have x times 0 be equal to something that's not 0. Yeah. So 0 is a rational number, but 1 over x can never be 0, and so everything still works out with this proof. Good questions. Right, once again, it's all about going back to the definitions. A rational number is one where you can write it as a over b with a, b in z, and b not equal to 0. It's exactly that and precisely that. But you have to do, in this proof, you have to do this additional step of showing that, okay, if I assume 1 over x is equal to p over q, then I get that x is equal to q over p. I need to show that p is non-zero. Why is p non-zero? Well, if p were 0, then 1 over x would be equal to 0, and that can never happen. So there's an additional step happening here. Oh my gosh, it's 10:04. Let's do one more. We have a little time for one more. Mahita, how are you feeling about contrapositive so far? Is it a little better? Okay, let's do another one, which will help us all even more. So let's prove that if n is an integer and 3n plus 2 is even, then n is even. Okay? And once again, let's first do a discussion. And what I want to make clear is that when you're writing formal proofs, you do not write this discussion. You only write the proof. But the discussion is very valuable for us talking and understanding the structure. So that's why I'm kind of making very careful pains to show you what belongs in a proof and what does not belong in a proof but is still a valuable mathematical discussion. Okay, so let's try to prove this directly. Okay, so if we try to prove this directly, then we say let 3n plus 2 be an even number. What can we conclude if 3n plus 2 is an even number? but we can only use the definitions, right? Being an even number just means that I can write 3n plus 2 is equal to 2k for some k. Only using the definitions here. If 3n plus 2 is equal to 2k for some k, then I can also conclude that 3n is equal to 2k minus 2. And then I can conclude that n is equal to 2k minus 2 over 3. But now I've possibly left the realm of integers. This isn't a very nice thing to say. Well, I mean, it's not an insulting thing to say. But this isn't, I can't conclude from the expression n is equal to 2k minus 2 over 3 that n is an even number, because this isn't even necessarily an integer, right? This doesn't even look like an integer. You could say that 3n is equal to 2 times k minus 1. That's exactly what is written here. We could factor things. All that I want to point out here is that, and this isn't the best example because contrapositive, I mean, you're all clever, and I'm sure that you can kind of find your ways around this obstruction. But all that I want to point out is if we proceed very naively and we assume 3n plus 2 is an even number, and then we start working as usual, then we get a little stuck because we end up with n looking like it's not even an integer. Whereas if we prove the contrapositive, things are much more straightforward. So the contrapositive, so proof by contrapositive, so we assume, so we show that if n is odd, then 3n plus 2 is odd. Here you have to trust me that the negation of an integer being even is that that integer is odd. Do we agree that this is the contrapositive of this statement? And now things will go more simply. We have to state that they are opposites. So you'd have to say, I mean, we're going to use the fact that if you want to negate an integer being even, that's equivalent to it being odd, and the negation of an integer being odd is that it's even. That is something that we can use at this moment. And this turns out to be easier to prove. So now let n be odd. What can I do if n is odd? Exactly. We can rewrite it as 2k plus 1. There exists a k in Z such that n is equal to 2k plus 1. Then 3n plus 2 is equal to 3 times 2k plus 1 plus 2, which is equal to 2 times, well, let me just write it out. This is equal to 6k plus 3 plus 2, which is equal to, I'm going to pull out a 2. So I'm going to get 2 times, I'm going to write this as 2 times 3k plus 4 plus 1. So I'm going to factor out a 2 of here, 3k plus 2 plus 1. Thus, 3n plus 2 is odd. And I have proved the contrapositive. So unfortunately, we're a little over, but what I want to point out here is that in some cases where a direct proof gets a little stuck, the contrapositive can end up being a much more straightforward way to prove this, right? Here we got a little stuck using a direct proof, but when we switch to the contrapositive, if we start with n being an odd number, then you can very easily manipulate 3n plus 2 to be an odd number in exactly this fashion. And so the contrapositive is a more straightforward thing to prove. Any questions on this? This is fine? Everyone's comfortable with what I've done here? Good. So, oh, yes?
And, sorry, where it says 6k plus 3 plus 2, which is equal to 2 times 3k plus 2 plus 1. Can you just walk me through where the 2 times that one, yeah, where that came from?
Right. So the point is I want 3n plus 2 to be odd. And by definition, that means I need to have 2 times an integer plus 1. So what I had is, after I kind of factored this out, I had a 6k plus 5, right? 6k plus 5 is what I had here. And I just need to massage this until it looks like 2 times an integer plus 1. And it turns out that if I rewrite 2 times 3k plus 2 plus 1, then this is exactly 6k plus 4 plus 1, right?
Oh, okay, I see. All right, thank you.
Yeah, all I did was I took this thing that I had and I massaged it using some factorization so that it was exactly in the form of an odd number according to our definition. So I could write this as 2k prime plus 1 if you wanted. Does that help?
Yes, thank you.
No, you won't have to use things that we haven't explicitly gone over in class. Okay, any other questions? I'm excited that we're a little bit past the logic and getting into proofs. This is where this class becomes much more enjoyable. All right, if there are no further questions. So remember, I have office hours tomorrow. If you can't make my office hours from 9 to 10, then send me an email. I'll be happy to meet with you at some other point tomorrow. If you have questions, if you're feeling nervous about the test, please reach out. And good luck studying and have a nice rest of your day. See y'all on Friday.
Thank you. Have a great day.